This video is a quick review of Chapter 7 from Fundamentals of Statistics. It covers the normal probability distribution. As a reminder, when you're dealing with a probability density function, which is used to compute probabilities for random variables, you must satisfy two properties. First of all, the total area underneath the graph must be equal to 1. And secondly, the height of the graph can never be negative. You can have probabilities of 0 or you can have positive probabilities, but no negative probabilities. And the area under the graph over any interval represents the probability of observing a value of the variable in that interval. In the past, we've dealt with uniform probability distribution. That's where x is equally likely for any two intervals, like rolling a 3 is just as likely as rolling a 5 if you're using a fair die. Now we're moving on to normal distributions. If you're using a continuous random variable, it is considered normally distributed if the relative frequency histogram has the shape of a normal curve. The normal curve is a single peak that will have inflection points on either side, one standard deviation away from the mean. The inflection point is the place where it changes from curving upward like a bowl to curving downward like an umbrella, or vice versa. The properties of the normal density curve are as follows. It is symmetric about its mean. There is a single point and highest peak at the mean, which is also equal to the median and the mode. The inflection points occur at the mean minus 1 standard deviation and the mean plus 1 standard deviation. The area under the entire curve is 1, and the area on either half to the left of the mean or the right of the mean is 1/2. As x gets larger and larger or smaller and smaller, it will come close to the horizontal axis but never touch it. And the empirical rule tells us how much area the curve is between equal standard deviations from the mean. So plus or minus 1 standard deviation from the mean encloses 68%, plus or minus 2 standard deviations from the mean encloses 95%, and plus or minus 3 standard deviations encloses 99.7%. Looking at the same properties of the normal curve, but more visually this time. The mean is in the center, which is also the mode and the median, and everything is reflected symmetrically across that line. Whatever's on the left will be reflected to the right and vice versa. Next, the points of inflection are at mu minus 1 standard deviation and mu plus 1 sigma, and that's where the curve changes from being bowl-shaped to umbrella-shaped and then bowl-shaped again. The area under the curve is equal to 1. And if you pick 1/2, either half, that area is going to be equal to 1/2. And finally, no matter how close it gets, it never actually touches the x-axis. The last property was the empirical rule. That's 68% within 1 standard deviation, 95% in 2, and 99.7% within 3 standard deviations of the mean. Remember, since the curve is symmetrical, you could take that 68%, split it in half, and know that 34% goes from the mean to -1 standard deviation and 34% goes from the mean to 1 standard deviation above the mean. One of the biggest concepts in this chapter is standardizing a normal random variable. If you're starting with a random variable that is normally distributed, you can standardize that by expressing it in terms of how far above or below it is to the mean in terms of numbers of standard deviation. That will give you a standard normal distribution, which has a mean of 0 and a standard deviation of 1. To accomplish this, when you have a data point, take x and subtract mu from it. That tells you how far above or below your average your variable value is, and then divide that amount by sigma. If you're typing this into your calculator, be sure to remember your parentheses. Put parentheses around the numerator, x minus mu, and then divide by sigma, so that sigma divides into the entire term instead of just the closest in proximity. Properties of the standard normal curve are very similar to properties of the normal curve, but now that we've standardized it, we know that our mean is going to occur at 0 and our standard deviation is going to be 1. So that's the only difference between that and what we looked at earlier for the normal curve. Again, visually we're dealing with the same thing as before, but instead of talking about mu and mu plus sigma or mu minus 2 sigma, mu is now 0, and instead of sigmas, we just deal with 1, 2, -1, -2, etc. There are two ways to interpret what the area under a curve for your random variable means. One is that is the percentage or proportion of your population with that certain characteristic. For example, what percent of cats weigh between 10 and 18 pounds? Find 10 and 18 on the cat curve and find out what the area underneath the curve between 10 and 18 is. The other way of looking at it is the same number, but you're just saying that's the probability that a randomly selected individual from population will have that characteristic. So if you randomly select a cat out of all the cats in the world, what's the probability it will weigh between 10 and 18 pounds? Again, you look at the curve and find the area below the curve between 10 pounds and 18 pounds. To determine the area under curve, you're going to look up your z value in a table. As you can see from the shaded figure, this table will show you the area under the curve to the left of z. Look up z going down the leftmost column. That will take you through the 10th digit of beyond the decimal point. And for the 100th digit, look across the top to pick the appropriate column. If you wanted to find a z value for 0.64, you'd look in the row for 0.6, the column for 0.04, and you would find that you have 0.7389 or 73.89% of your area is under the curve to the left of z equal to 0.64. Occasionally you might encounter z sub alpha. This is the z-score necessary so that the area under the curve to the right of z sub alpha is equal to the value of alpha. Let's suppose someone wanted z sub 0.33. Look on your z sub alpha chart and find the nearest value to 0.33 and determine that the z-score that has 0.33 under the curve is 0.44. So z sub 0.33 is going to be equal to 0.44. If you don't have a chart for z sub alpha, it is not a big deal. If you know the total area under the curve is 1, then what isn't to the right of the curve must be to the left of the curve. So if you want to know the z-score when the right of the curve has 0.33 under it, just go look for the standard z-table and find when you have 0.67 to the left of the curve, because if 67% is to the left at z equals 0.44, that means 33% is to the right at z equals 0.44. A quick example of how to find areas under curve. Golden retrievers have an average weight of 60 pounds and a standard deviation of 10 pounds. What percent of golden retrievers weigh less than 66.4 pounds? First, you want to figure out what your z is going to be. So z is equal to the value of x, which is 66.4, minus your mu, which is 60. And all of that is going to be divided by 10, your standard deviation, to give you a z of 0.64. Then you're going to look that up in your z-table and find out for 0.64, there is 0.7389 under the curve. In other words, 73.89% of golden retrievers will weigh 66.4 pounds or less. Sometimes you'll be given a percentage or probability, and from that you're going to want to determine what the value of your variable is going to be. Let's use the same example as last time. We have golden retrievers with an average weight of 60 and a standard deviation of 10. We want to know at what weight will 85% of retrievers weigh less than that weight? In other words, what's the 85th percentile? First, you need to find out where you're going to have 0.85 under your curve. So look at your z-chart and find the closest to 0.85, which here is going to be 1.04. So your z is 1.04. When that's the case, the area under your curve will be 0.85. You're going to take that z, 1.04, but you also know z is equal to x minus mu over sigma, and you know mu is 60 and sigma is 10. So now you know 1.04 equals x minus 60 all over 10. Multiply both sides of the equation by 10, and you get 10.4 is equal to x minus 60. If you add 60 to both sides, you get x equals 70.4. That means 85% of golden retrievers will weigh less than 70.4 pounds.